In our second section of Chapter 8, we are going to be tackling what is described as inverses of relations. So check out our learning goals. We're going to find out definitely, find inverses of relations. Right now, we know what a relation is, but we really don't know what their inverses are. We're going to apply some of those properties of inverse relations and functions that we were working with in the past. And we want to make and interpret graphs of inverses of different relations. So, sounds like we have a little to do, but let's get started. All right, a couple things. Let's go back and describe what we said our relation was before we try to talk about our definition of inverses, which is there for you. A relation, we said, a good definition, is any set of ordered pairs. So it doesn't matter what those ordered pairs are. It doesn't matter if any of them repeat. As long as they're a set of ordered pairs, we have a relation. And that set of ordered pairs could be graphed. It would graph into all different types of situations, shapes, curves, etc. So if we're talking about a relation, is any set of ordered pairs, and remember we last talked about relations when we were talking about functions. So there was a relationship between the x and y values. Now, if we say a relation is any set of ordered pairs, then when we talk about the inverse of a relation, you definitely want to switch your x and y values. So if I had an example of a point, we should be able to do it with a point. If I had a chart, and when I'm talking about a chart, like an XY table off of your calculator would be a good way to think of that. If I had an equation, we want to talk about how you would handle an equation. We're going to do all of these today. And then how do you also find an inverse of a graph? So let's start with just some points, and then we'll review. If my point is 3, 4, as I have here, and we follow the definition of inverse, then it'd be nothing more than switching the x and y, and so 3, 4 would become the new point 4, 3. So 3, 4 is the original, and 4, 3 is its inverse. And you would do that on any set of points you have. So in an xy table, when you know you have numerous xy values, if you looked at that, that would be the original. If you did the process of switching the x and y, then you would be looking at the inverse of the original chart or table. Now, the only other thing that I want to remind you about is we've also had some new notation. We had the f of x, which we're familiar with. If we add the little -1 exponent, you are definitely thinking of I am the inverse. That is your new symbol. And actually, it's not that new, because I believe even on the next slide, I think I talk about matrices. Oh, not on this slide. I'm a little ahead of myself. But here we go, a relation. A relationship between two variables such that each value of the first variable is paired with one or more values of the second. And the key piece on this, if you go back and look at it, we had a function definition earlier on, and it was very similar. I believe it said a relationship between two variables such that each value of the first variable is paired with exactly one value of the second. So you can only have each x could be corresponding to one y. Now we're saying anything goes, because each value of the first is paired with one or more values of the second. So I could have 1, 3, 1, 3, 1, 4, 1, 5, 1, -8, 2, 5, 2, -8. Anything works if we're in a relation. So see if this makes sense based on our previous definitions, and that is all functions are relations. So every function that we used to talk about is a set of ordered pairs. But all relations, any set of ordered pairs, are not functions, because in order to have a function, you have to have a specific characteristic of things going on in your ordered pairs. So that's a good true and false question. All functions are relations, but all relations are not functions. So let's try on this one first. State the domain and range of the function. And if we did that, you remember our definitions, hopefully. Yes, yes. Domain, all possible x values. Range, all possible y values. So our domain in number 1, 1, 4, 2, 9. You do not have to put them in order. You can leave them in the order that they're there. Our range, our range, 2, 5, 6, and 0. If we would have any that repeat, you do not even have to list them twice. Once you list it and it's part of the set, you've done what you need to do. Now let's look and see here. I have a little, extra arrow. And let's see what we're going to do with that extra arrow. So now if I would take the question and change it slightly to state the domain and the range of its inverse. Oh, so then you got to be thinking, what's its inverse? Ready? And based on our definition, state the domain of its inverse. You're not going to do them both at once. We'll do them one at a time. So state the domain of the inverse. Well, the domain on number 1 again is the domain of the inverse would now be 2, 5, 6, and 0. The range of the inverse would be 1, 4, 2, and 9. So I've left a couple others that we can talk about in class to see if you really have some issues and to see if you really caught on to the concept. So you should be able to look at a set of ordered pairs and not have to rewrite it and tell me what's the domain and range of the original and also what's the domain and range of an inverse. So this should look familiar. When we were talking about functions previously, we said, does the table represent a function? Why or why not? And as a quick review, we were saying, each x has to be paired with one and only one y. So you were looking for x's that repeated was your first thing. So 5 is with 8, 2 is with 6, 4 is with 6, and 3 is with 2. There is not one x that repeats, so this was, yes, I'm a function. Okay? And so we should have had down here a yes. Okay? With that, 5 was with 8 in the second one, 1 is with 6, 1 is with 6. We're just repeating the same dot, like we go back to it in a drawing or something like that, and 3 is with 9. So again, yes, this is a function. Then we go to the last one. 5 is with 8, 5 is with 6, 4 is with 6, 0 is with negative 2. So each x has to be paired with exactly one y. So we have a slight problem right here. 5 is with 8, and then 5 is with 6. So when we saw that, we should have been raising a little alarm and saying, wait a minute, something's up. 5 is with 8, 5 is with 6. There's a problem. And because of that problem, then the answer to our question here should be no. Okay? So does the table represent a function? Why or why not? So those are just normal functions. So again, just like in the last one, let's pull out a slightly different question. Does the inverse represent a function? Why or why not? Oh, okay, so now you have to look at it under a different light. And doing that, think about what your inverse definition was. 8 is with 5, 6 is with 2, 6 is with 4, 2 is with 3 would be the first combination you're thinking of. So is that combination representing a function? And you would say no. So I got the purple versus the pink. Not a big distinction there, but no. Go to the second one. 8 is with 5, 6 is with 1, 6 is with 1, that's just repeating, and 9 is with 3. So do all your domains have exactly one y value? I believe we had a yes on that one. Then, last but not least, 8 is with 5, 6 is with 5, 6 is with 4, negative 2 is with 0. What are you going to say there? Hopefully it's a big fat no. And the problem again is not the top two this time, but the middle. 6s with 5, 6s with 4, that's two different values, can't have that. It says must be paired with exactly 1 to be a function. So see what you have to do? You just have to do that switch in your head and you should be good. Now we also had something when we were dealing with functions called the vertical line test. It was definitely a shortcut. It allowed you, without the x and y's in front of you, on a graph, to test the picture of the graph and say, is it a function? And again, we're talking about if it's a function, each x has to be paired with one y. So you have to have each x being hit once. If it gets hit more than once, it was not a function. So when we say get hit, so we'll take our vertical line here and we'll move it through our graph. Is there anywhere in this graph that our vertical line hits the graph more than once? Down here, is there anywhere in our graph that hits more than once? Going up here on this parabola, oh, we got some problems on this one. Almost every place in it, it has two intersections. The only place it doesn't is right there at the vertex on the side. Here, I think we're pretty good. Only one time all the way through. And then here, ooh, we're starting to see some problems. Not only does it have 2, it has 3 in some spots, like right there. So you should be able to go through and say, does this graph pass the vertical line test? If it passes, that means that that graph is a function and has only one x value for every y. Again, though, let's think about our inverses. And if we did that, let's reset the page and pull out our question this time. Let me pull it out this way. Here we go. And this time, now we want to talk about the horizontal line test. Oh, that's a little different. Now think about it. The horizontal line test would be left to right. It would be testing the original graph, and it would be testing whether the inverse of the original graph is a function. Why? Because we're going left to right, which is the y values, and we're checking those because they would now be in the x slot if we did inverses. And so this time we need to pull out a horizontal line. And let's do that, and let's run it this way. So my little S curve, every time we're looking, it's getting hit once and once only. So the inverse of that S curve is a function. Let's go to our diagonal line. Again, anywhere you place this horizontal line, it got intersected once. So the line's inverse is a function. Let's go up to the sideways parabola, running it through. Now remember, it's never going to get totally straight, so we're good, we're good, we're good, we're good, we're good. Again, we are fine. It is a function. Coming over here to our loop-de-loop, up and down, we got a problem. 2 intersections there, and sometimes we're even getting 3. So its inverse would not be a function. And then last but not least, the parabola that was opening downward, again, has some problems. The only place it doesn't is right there, but everywhere else, so that makes it bad overall. So our horizontal line test shows us that it is the inverse is not a function. So you can test graphs very quickly with the horizontal line test. But remember, you are not testing the graph that you're looking at. You're actually testing the inverse of that graph, which is the one you can't see, the one you would get if you flip-flop x and y. That's what you're really assessing. All right, so we did points, we did charts and tables. Now let's just run this one again and see what happens. You know, I might save this one for class and see if we really got the idea of vertical line test. So start looking at those and think what you would say. If each of those, the question was, is this graph a function? Or does this graph represent a function? And then does its inverse graph represent a function? And tell me what you would do and why. So it's a good one to save for class. All right. Now let's go to talking about an equation. We did points, we did tables, we did graphs. What about an equation by itself? Well, is the equation a function? We did basically the idea of you could take points, put them in, graph it, run your vertical line test. But what if we want to just know what is the inverse of this equation? So let me put a little dividing line here. And I do that for, we're going to say, this is the original. Okay. So now the question is, what is its inverse? And since we don't have points, so to speak, we can't just flip-flop x and y. But using that same definition, we can get closer to what we need. So let's flip-flop x and y in our original equation. So copy as is. The only change is x is now in the y slot, y is in the x slot. That's the only change we're making. Okay, with that, you know that that's a pretty good looking equation. You say, oh yeah, that's the inverse. No, it's not. We can't tell anything from that. We're so used to having our equations in y equals form for graphing, for substituting, just a lot of our algebra problems. It's so much simpler. It's called standard form. Slope-intercept. It's not standard form of a line, but it's pretty standard for our work. Now, so that means we really need y by itself like we had over in the original. So let's take this equation as is, and let's get y by itself. Do our algebra steps, rewrite it, get y by itself. Y is connected to the 3, and also there's a negative 5, so I think our first step needs to be add 5 to both sides. And if we did that, x plus 5 would now equal 3y. And we've got 3y. We need y by itself. So how do we undo a times by 3? Well, with a divide by 3. When we divide by 3, we now have a new equation. Y equals, if you want to subdivide it, you would have had x over 3, or 1/3 x, some people like to have, plus 5/3. So that is truly in slope-intercept form. You can say, hey, my slope is 1/3, and my y-intercept is 5/3. And you compare that to what you had originally. My slope was 3, and my y-intercept was negative 5. They are definitely not the same equation, but this is now considered the inverse of our original. That's the inverse equation. Remember, just flipping x and y wasn't good enough. Okay? You had to, from there, rewrite it and get y by itself. That's the key piece for writing an inverse of an equation. I don't remember what I had down here, so how do we do a graph? That's what I think we're going to see next, maybe an equation. What about the graph of that inverse? How would you make a graph of that inverse? So that's where we'll head, and that'll be our last piece. So let's use that same equation, y equals 3x minus 5. If I would ask you to graph the inverse of that equation, well, there's no way you're going to do that from face value, but based on our definition of flip-flop x and y, I think you could. But you don't have to use the equation. We want the graph. So ready? We would take some points like normal and get it graphed as is. So as an example, we always work on putting some positives, some negatives, and some zeros. So pick a few, and if we just stay nice and small, negative 2, negative 1, 0, 1, and 2, we put them in. Put a negative 2 in, times it by 3, that's negative 6. Subtract 5, we get negative 11. Negative 1 goes in. 3 times negative 1 is negative 3. Negative 3 subtract 5 is negative 8. 0 times 3 is 0. 0 subtract 5, negative 5. 1 times 3 is 3. 3 subtract 5 is negative 2. 3 times 2 is 6. 6 subtract 5 is 1. So we're getting our ordered pairs there. And looks like we have pretty close to just what we need if we still keep it by ones. So let's now graph the original. And when we graph the original, and it may say graph the original and its inverse, or it might just say graph its inverse. Maybe let's go with just graph the inverse. Well, you have the original there. You didn't have to rewrite the equation. You didn't have to do any of that. We just found values for our original graph. Instead of graphing the original, let's just graph the inverse. We will take only those values, but we can't graph them as is because that would be the original. The definition was? Good. Flip-flop x and y. So if we flip-flop x and y, we should be good. And as I said, I think we're just close to having the right amount. So we need to go negative 11. If each of these are by 1, we're down here at negative 11, down negative 2. There's our first point. Negative 8, There's 5, 6, 7, 8, down negative 1. Then we're at negative 5, 0, and then negative 2, 1, and 1, 2. We could then take our ruler, make our line, put arrows on the end of it, because that's exactly what we're looking at here. And mine's a nice light blue one. Run it through all of them as best you can. And that would have been our original, or sorry, that would have been our inverse. And if you do need the original on there as well, let's go back and change colors for that. We could also put that on. So we could do a negative 2, negative 11. We'd be down in here. A negative 1, a negative 8. A 0, negative 5. A 1, negative 2. And a 2, 1. So you can see that with this one, and let's change the line color on this one as we draw our line. Our original is in pink, purple, and our inverse is the other. So if they want them both, you can put them both. If they just want the inverse, you'd graph just the inverse. Notice, we're not changing the equation. We just took the original, took those xy points, and we flip-flopped them using our definition to flip-flop, switch the position of x and y. So that's all you need to do. You've seen how to take and find an inverse of a point, a chart, an equation, and a graph, all in this section. And I'm sure you're going to be doing a few of all those different types. All right. Bring any questions and be ready to discuss those horizontal line tests, vertical line tests with those couple examples in class.